Good morning students, welcome to 15th video on system of particles and rotational motion. So in this video we are going to consider the last concept of this chapter, which is rolling motion, and later expression for kinetic energy of rolling motion. So let us know what is rolling motion of a rigid body with respect to an axis. So consider a circular disc of mass m of radius r, which is capable of rotating with respect to an axis with a constant angular velocity omega. This is a circular disc of mass m with a radius r, capable of rotating with respect to this axis of rotation with a constant angular velocity omega. When the disc is rolling on the surface, because it is the case of rolling motion, then the velocity of center of mass moves in linear path. So therefore, the disc will have translational velocity, which is the velocity of center of mass. If Vcm is velocity of center of mass, then center of mass moves in linear path, therefore velocity of center of mass is given by r omega, where r is radius, omega is the angular velocity with which the body rolls on the surface. So the center of mass moves with a linear velocity, which is called as velocity of center of mass, Vcm equal to r omega, which is parallel to the surface. Now, if I consider a particle which is at the bottom of the disc, which is just touching the surface, when this disc rolls on the surface, so I have chosen a particle which is just touched to the surface, and if v is the velocity of the particle which is at p naught, then its velocity is given by v is equal to vr, velocity of the particle at the bottom of the circular disc which rolls on the surface, which is equal to Vcm, which means the particle at the bottom will move with the same velocity as that of the velocity of center of mass, which is equal to r omega. Now if you choose, of course this is the condition of the disc which rolls on the surface. Now if I choose another particle, say E1, which is at the top of the circular disc, which has a velocity direction in the same direction as that of the velocity of center of mass, and for that we write velocity v is equal to vr plus Vcm. Vr is velocity of this particle, linear velocity of this particle, plus the velocity of center of mass, because for this particle which moves in the same direction as the velocity of center of mass, therefore the velocity of the particle at the top of the disc is Vr plus Vcm. But we know Vr is nothing but r omega plus Vcm. Vcm is also r omega, therefore velocity of the particle at the top of the disc is written as 2 times of Vcm, or 2 into r omega. R omega is velocity of center of mass. Thus, a particle which is at the top of the circular disc will have a velocity which is twice that of the velocity at the center of mass, or which is twice that of the velocity of the particle which is at the bottom. When again this particle comes at this point, it will have the velocity 2 times of the velocity of center of mass, and this particle will have the velocity equal to velocity of center of mass. So this will rotate. So this is the rolling motion of a rigid body on a surface, in which it rolls with respect to an axis of rotation with a constant velocity, angular velocity omega. So now let us see the expression for kinetic energy of a circular disk which rotates with respect to an angular velocity omega. See, we know that the kinetic energy of the translational motion is given by k is equal to half m vcm square. General formula is k is equal to half mv square, but v is replaced by velocity of center of mass in this case. So translational motion, the circular disk will have a kinetic energy which is given by k is equal to half m vcm square. Similarly, we know that the kinetic energy of a rigid body capable of rotating with respect to an axis with a moment of inertia I and angular velocity omega as k is equal to half I omega square. So as this rolling motion is the combination of translational as well as the rotational motion, therefore total kinetic energy of the circular disk which rolls on the surface is given by k is equal to kinetic energy of the translational motion, that is half m vcm square, plus kinetic energy of the rotational motion, which is half I omega square. So this is the kinetic energy of the translational motion, this is kinetic energy of the rigid body with the rotational motion, and this is the total kinetic energy of the rigid body in which the velocity of center of mass is having translational motion, and this because of the disk rolls with respect to an axis of rotation with an angular velocity omega, it has rotational kinetic energy. So since moment of inertia I is equal to mk square, where k is radius of dilation in this case, and angular velocity omega is equal to velocity of center of mass vc divided by r, because we know v is equal to r into omega, then this equation becomes, so I will call this as equation b, then equation b becomes k is equal to, I will keep the first term as it is, r 1 vcm square plus half, instead of this I can write m k square plus, not plus, into omega square here, into omega square is nothing but vcm divided by r whole square. So it is vcm square divided by r square. If I take half m vcm square as common, then right here the expression for kinetic energy as half m vcm square. I will take this as common factor on this term. So then what I left is 1 plus, in this case I have taken half m vcm square as common. So then what I left is 1 plus k square, which is in the numerator, divided by r square. So this is the expression for kinetic energy of the rolling motion in which a rigid body capable of rotating with respect to an axis is given by k is equal to half m vcm square into 1 plus k square divided by r square, where k is radius of dilation, r is radius of the circular disk, vcm is velocity of center of mass, and m is mass of the circular disk which is capable of rotating with respect to an axis of rotation.